All right. Good afternoon and good evening, everyone. So my name is Melike Erol-Kantarci. I'm a Canada Research Chair in AI-enabled next generation networks and an associate professor at the University of Ottawa. So I'm giving this seminar today, which is entitled Recent Advances in Smart Grid Communications as an IEEE Comsoc Distinguished Lecturer as an invitee of the Sacramento chapter. So thank you very much again for your invitation. We will talk about two things today. One would be recent communication techniques, and the other one, the advances in smart grid in relation to communication technologies. So they're closely intertwined, but first I want to start with introducing how communication technologies transformed and are transforming smart grids. So it was 2007 when for the first time, the word smart grid was pronounced by the President Obama. And after that, there was a surge in research. The smart part of the grid, as we know it, comprises mostly of integration of ICT technologies to the power grid. As many of you know, power grid is one of the most complex man-made systems. And its monitoring capabilities before smart grid was not very strong or was not at its best. So for example, if the crews were to read meters, they would go to the premises of the customer and read the meters. So there was no communication technique to bring those measurements remotely to the headquarters. Likewise, demand response, it was implemented in the form of load curtailment for large customers. For example, there's an industrial region and you want to reduce the load because there's a peak load and it can cause some harm to the grid, then load curtailment or demand response would be implemented, but it would be only one way. A lot of the things did not include the beauties of information and communication technologies. And as we all know, I mean, these technologies, ICT technologies, advanced so much in the last 10 years that impacted a lot of fields, it was almost inevitable that they would not impact the power grid and make the grid smart and smarter, actually. So it's an ongoing process. In 2009, 2 years after this announcement, I started doing research in this area. And since then, I've been working on it, sometimes more on the communication side, sometimes more on the optimization of the power grid side. And it has been a fantastic area of research because there are many unaddressed problems. But before we get introduced to those problems, I want to introduce a couple of the applications that has emerged with the smart grid and transformed by the help of ICT. Number one is advanced metering infrastructure, or AMI, as we call it for short. This is where the crews stopped going into the households, the premises, to read the meters. So two-way communication started, and that helped a lot from saving work hours for the operators' utilities. Demand response, especially demand response for homes, is another very interesting and exciting area. As I said before, in the earlier days, demand response, or sometimes we used to call it load curtailment, was a thing for the industry customers, large consumers, because it makes sense to curtail their load rather than, maybe calling every household, asking people to stop their washers. I mean, can you imagine? It's very, very difficult to do it if you don't have ICT in it. But now with the ICT, what can be done is a signal can be sent to the meters. Appliances, smart appliances, may take the signal and reduce their consumption. And even you can provide price incentives to the users or some other peak load reduction incentives, and they would reduce their consumption. Of course, a single household wouldn't matter much for a utility, but if you do it in a whole neighborhood, if you can enable this in a neighborhood, it really matters, actually. The other thing that has become possible with ICT technologies in the smart grid was situational awareness. In the prior days, and we still do have SCADA. SCADA is the monitoring tool that is used in smart grid and several other industries. But with the smart grid, the use of PMUs, phasor measurement units, and more detailed measurements from the field was obtained, and that gave a bigger visibility or more detailed visibility to the utilities in managing their assets. Another thing that almost became popular in the same time with smart grid is the electric vehicles. So there has been a lot of hype around electric vehicles, that they're zero emission and all those things. Well, number one thing is electric vehicles are powered from the electricity grid. So whatever the grid is using, coal, solar, wind, that is the source of power for the electric vehicles. But aside from the source of electricity, when does the charging happen for an electric vehicle? At what point of time or where in the grid are these electric vehicles get connected? If there's a neighborhood where there's a huge load and somebody tries to plug in their electric vehicle, then that might create some problems. So how we do that integration, that can be solved quite nicely with ICT. Renewable energy integration is another thing, and actually that's one of the pillars of smart grid, that why people started getting so excited about it. Up until then, I would say the end of 2000s, of course, we had solar power generation capabilities, wind power generation capabilities, but the problem is that they are intermittent. They are still intermittent. Nothing changed in terms of that because it's the nature that provides the sun and the wind power. But what has changed is that they now have communication capabilities so that whenever their production or generation is less, they can send a signal and another diesel generator, for example, can kick in. So that made the integration of renewable energy easier. And then finally, which is a topic that I'll come back later in this talk, the emergence of transactive energy systems. So transactive energy systems are born out of microgrids and peer-to-peer energy trading among microgrids, which means essentially, for example, you are in your home, you have solar panels, you're generating surplus energy that you're not using. You don't have any load to use it. You can store it, but another option is that came with smart grid is that you could sell it to your neighbor. You could provide it or sell it. And transactive energy systems is about that. So there is some exchange of energy either between the customers or from the customer to the utility. Now we're going to talk about these, and these are really interesting things. But then let's talk about the communication technologies, because we want to look at the enablers, what enabled those kind of innovations in smart grid. So as the state-of-the-art communication technologies, there is a big array, and much more than I included here, big array of technologies that we can look into. One of the recent ones is private 5G or private LTE. And it's not only transforming the smart grid sector, it is used in mining, many other critical places, public safety, or smart factories. It is a topic of discussion, that how we use private 5G or LTE networks. LoRaWAN is another technology, especially born out of IoT needs. So if you think about smart grid, there's going to be a lot of assets out there, right? Smart meters, maybe smart appliances, electric vehicles, solar panels. All of these can be considered as IoT devices. So any kind of IoT technology, likewise narrowband IoT, could be a potential solution for smart grids. And I'm going to talk about these technologies as like they could be, they can be, because there's no standard. I mean, there's nothing telling the utilities, okay, that's the standard communication protocol that you're going to use. Every utility is free to choose whatever communication technology they want to choose. And RF mesh is on the older side, so more than state of the art. I mean, it has been there for a very long time. Private RF mesh networks has been used. PLC, which is again another hot area, power line communications, that is for low throughput communications between the smart grid assets. Again, for monitoring control applications, it has become popular. And then the rest of it, I guess all of you are familiar, like Wi-Fi. We use it for home connectivity all the time. But once you start connecting your smart appliances or your electric vehicle and they use your home Wi-Fi, then that's a technology actually helping smart grid as well. Zigbee is a low power personal area network technology that is used in sensor networks. Ethernet, we all know, but maybe we started forgetting about it because it's getting an old technology. Wi-Fi is replacing all the cables. Optical on the long haul, always when we need capacity reliability, is something that we resort to. And satellite for remote areas is a go-to technology usually. So as you can see, there's a mix. It's like a bag of technologies. And if you want to connect your assets, then you have to look at the particular application, your particular location on the world, your cost. Like for example, fiber has a huge cost. Satellite has a huge, all pros and cons. So I'm not going to say like this technology is the best. This should be the communication technologies for any smart grid, because there's no such answer to such a question. But rather than that, I'm going to talk about what's in the future for communication technologies, and then come back to what exciting things can be done with these communication technologies. Nowadays, so if you know my background, I also have a leg of research in 5G and 6G. So smart grid is an area that has been dear to my heart for a long time, and it is still. But I do a lot of research in 5G and 6G communications. And with this, we are seeing some exciting times. So if you ask like when 6G is going to be a reality, we are targeting 2030 for this. So it's usually 10 years after the previous generation. And if you ask people in the communication world, what's 6G going to be like, you can find many answers. There are countless answers to this question, but probably the ones that emerge from many of the people are that, number one, we will have more diverse set of users and verticals. We're going to have context and semantic information somehow embedded. But more important than others, and something more pronounced than the others, is being AI native, having stronger network automation. So that's where the AI techniques come into the picture for communications. And we also see AI machine learning penetrate into smart grid as well. So today I'm going to talk about these two things like the two sides of a coin. At one side of the coin, we have the communication technologies empowered by AI. On the other side of the coin, we have the smart grid technologies empowered by AI, and they're mutually empowering each other. So I get asked a lot, so I want to clarify one thing before we go into further details of the techniques. You talk about AI and you say like you do AI-enabled research. Is it AI or machine learning? Now, first of all, what is AI? What is machine learning? Artificial intelligence is the umbrella term that covers everything we do for making machines as smart as humans, or as much as possible. Making machine intelligence close to human intelligence. Machine learning are the set of algorithms that tries to give this intelligence to the machines, but there are 4 different types of categories under machine learning, and they all probably model a different side of human intelligence. It's not so easy to get to the human intelligence. Number 1 category is supervised learning, where we work on labeled data. Number 2 is unsupervised learning, where we have unlabeled data, but we try to find out the patterns in a data, similarities or differences in a data. Number 3 is reinforcement learning, which is a technique that I work on a lot, and today is going to be one of the topics of today's talk. It's about control side of things. So for supervised and unsupervised learning, we talk about having data and looking at the data to either classify or cluster. But for reinforcement learning and deep reinforcement learning, so there can be deep learning for classification or deep reinforcement learning on the control side. And these are 2 different things. But whenever we have reinforcement learning, it touches upon control of something. So we can control the smart grid, maybe using reinforcement learning. We can control the communication systems, maybe using reinforcement learning. So we're going to try to find out answers for these questions. So first of all, we said AI techniques are trying to mimic human intelligence. And reinforcement learning techniques particularly focus on one aspect of human intelligence. That is the interactive learning process. So as a child, none of us is born with a handbook of rules around us, right? I mean, don't cross the street, don't climb up a tree, don't do that. No, our parents teach us some of the things, or some of the things we just learn by trial and error. Like you climb a tree, you fall, or your mom yells at you and you never do it again. Or maybe you do it. that really depends. But by trial and error, and it's not humans, by the way, we have similar intelligence in animals as well. And that has been, studied by Pavlov in the past century a lot. But today we're going to talk more about the human intelligence and put an agent in the place of a human, where the agent will try to interact with the environment and learn the outside world. Now, here we have an agent that looks like a robot. There's an environment which is too generic, I know, but as we go into the depths of the problems that we're talking in smart grids and communication systems, that environment will become more clear to you. But for now, let's start with the generic definitions. So in reinforcement learning, we have an agent. Agent interacts with the environment. That interaction is called an action. Every action causes the agent to change its state to the next state, and the agent receives a reward. Now, this reward is very, very important, because without the reward, the agent doesn't know whether it's doing good or bad. There's no way of evaluating the actions. So this evaluation and numeric evaluation gives us the opportunity to find the best policy. Now, what is a policy? Policy is a sequence of actions. And I think the best example for this is the game of chess, or any board game. But I'm going to use chess as an example. So you start with some initial moves, and then your opponent does some other moves, and you keep following a strategy. You keep forming a strategy. Sometimes you win, sometimes you lose. Whenever you win, that means you're executing an optimal policy, or at least a policy that's good. In reinforcement learning, when a machine executes reinforcement learning, it has to do it in multiple episodes. So it's not just one time of chess playing and then the machine becomes suddenly intelligent, but the machine has to play thousands, maybe millions of times these kind of games. And out of the possible winning strategies, it has to choose the best ones. On the right-hand side of the plot, what you're seeing is the bolded lines are the optimal policy, and the other ones are the potential policies. Now, I'm going to do a very quick description of Markov decision process. I'm not going to spend too much time on the math of this, but we just needed to define the reward function, which is, as I said, very, very important in reinforcement learning. And then I'm going to show you examples where we use reinforcement learning in smart grid and then in communications as well. ST is the state of an agent at time t. AT is the action that the agent takes at time t. So how does the agent receive the reward? In state ST, the agent takes an action AT. The clock ticks and reward RT+1 is received, and the state moves on to the next state, which is ST+1. If we are talking about a deterministic system, always we switch from ST to ST+1 for certainty. So there's the probability is 1 going there. But if we're working on a non-deterministic system, then there is a probability that we may land on a different next state. So that next state probability that you see here defines that phenomenon. Then there's also a chance that we don't get the same reward. It depends on how the MDP is designed. And if you think of a gambling machine, for example, I mean, I don't gamble, but everybody knows, I guess. Every time you do a bet, you may get a different reward, because otherwise it would be too simple to win. So there is a reward probability as well. Now, episode is the trial of actions, like from the initial state to the goal. And then the policy is the thing actually that we want to obtain at the end of each episode. Now, there has to be a good policy and a bad policy. How do we define a good policy? Now, the good and bad should be, in our world, has to be determined by numbers, right? We have to give a number to each state's output, which is actually the reward. So a reward is a numeric value, and the expected value of the summation of the rewards gives us the value of a policy. This is what you see in this formulation, plus something else too. You have the gamma here. The purpose of the gamma is called the discount factor. It's between 0 and 1. And this is a definition that we use for infinite horizon games, where we want to degrade the importance of future rewards. If it was a finite horizon game, I could just add up the rewards and say, this is my expected reward. But for an infinite horizon game, because, if you play chess, we do 100 moves, maybe you don't want your 100th move to be as impactful as on your first move in the game, because that's going to come in the future. Your opponent will take other actions. So it shouldn't be that important, right? With this discount factor, we are actually degrading the importance of the future rewards. Now, if you organize this term, the expectation, in some form, if you do some algebra on it, which Bellman did for us, Richard Bellman, he is a person who formulated the MDP as an optimal control theory problem. He came up with this equation that can be solved by dynamic programming. As you can see, the beauty here is V star ST is dependent on V star ST plus 1. So as the future policies, future values of the policies, if you can insert them in an iterative fashion, you can calculate the value of your final policy. Now, the trick is we have next state probability here. To be able to use dynamic programming, we have to be in a known environment. So, for example, in robotics, people usually work in known environments. You have a cup to hold, that is a known environment. But in wireless or smart grid, we usually work on an unknown environment where the probability of the next state can be different. And for that, we have a solution too, so we're not stuck. We have something called model-free learning. Model-free learning relies on the idea of temporal difference equations, which is an idea that came from Chris Watkins around at the end of 1980s. And the idea is that you approach to a certain value. So you have a Q table, you scan the Q table, and that technique is actually the Q learning technique. You scan the Q table, and then you try to find the good values, and you try to find the good direction that's going to give you good Q values. So this actually Q learning technique, it has been used in many fields, in smart grid and smart grid communications, 5G, 6G, all around the place. It is one of the simplest algorithms to implement, but it has a problem. We're going to discuss about this problem, but before that, you might be thinking of another problem, which I need to say that we got a solution for, and that is what we observe in any kind of optimization problem. How do we avoid getting stuck in the local optima? Now, for Q learning, we have something called exploration and exploitation, where the agent sometimes takes a risky action, and that risky action may turn the rewards in a certain direction, which is much better than the previous direction, and the agent tries to exploit this fact. There's a very famous algorithm that is used by many researchers, which is called epsilon greedy. So with a degrading value of epsilon, and epsilon is already a small number, we take a risky action. So we allow the agent to take a risky action. And as the time goes by, that epsilon is degraded. So with less and less taking risks, we try to find the optimal values. Actually, there's a funny story about this. At one time, and these algorithms, by the way, are used a lot or have been used a lot in game playing machines. So Google's AlphaGo machines, chess machines, IBM's backgammon machines, they all rely on reinforcement learning, but more advanced algorithms, of course, and some of them we're going to talk about. So at one time, Google Mind researchers noticed that their chess playing machine did something wrong. And they were worried. Oh no, it's going to lose the game to a human player. But then what happened is the machine won the game. And at that time, the machine was actually doing exploration. So it took a risky action. Maybe the immediate reward was not very good, but then in the end, eventually it found out better rewards and it led to a winning strategy. So this is a solved problem in Q-learning, but a different kind of problem that gives us a headache is that in temporal difference equations, which we use in model-free environments, which is almost most of the problems that we're working with, that Q table can grow very large because Q table just has states and actions. So if you have a lot of states and if you have a lot of actions in a problem, we're going to end up with a huge Q table where we have to store and then scan through each time. So instead of this, some people came up with really smart algorithms, smart ideas to solve this. And one of them was actually, relying on a very simple idea that you have a huge data set. What do? You do estimation, right? You can put some curve. Well, the simplest is linear regression. But with linear regression, you can't really model the data too well. You probably want to have a few more parameters and then filter the data somehow. Or best of it, you can have a neural network, right? Neural networks works as filters. So you can put a neural network in front of or behind reinforcement learning to drive the Q tables. Now, a sneak peek into neural networks, just thinking that some of you might not be experts in this field, but of course not a very comprehensive coverage. So the field of neural networks started with perceptrons around 1950s, and perceptron was a concept put forward by Frank Rosenblatt, where we have a decision circuit. The perceptron is actually a decision circuit. It has inputs and an output. And as you can see, multiple inputs are going into one output. So this is like a classification. This can be something leading to a classification problem. Now, the weighted sum of the inputs are passed through a function, which is a threshold function, as we see over here on the right-hand side. If the weighted sum is less than a threshold, the output is 0. If the weighted sum of the inputs is greater than a threshold, then the output is 1. So this very, very simple activation function of the old days changed a lot in neural networks. We use much different activation, much sophisticated activation functions. Plus, this is just one perceptron. Now we have very advanced architectures that we can organize neurons in different layers. But let's go step by step. So when we put the neurons in two layers, input and output layer, that's something called a shallow, well, we don't usually say shallow neural network, but in contrast to deep neural network, that's a shallow neural network. For a deep neural network, we have just the hidden layer in between. It can be one hidden layer, it can be hundreds of hidden layers. It doesn't really matter. And what we're trying to do by neural networks is that we're trying to estimate the weights. So you see that weight factor over here in the perceptron, or the weight factors on the links that are going through the layers of neurons. These are the things that we are trying to learn in our prediction estimation problems. Now, so far so good. We have a neural network, basically a filter to estimate the Q table. Then how can we use it for reinforcement learning? If you just put the neural network, then the reinforcement learning agent, can this be helpful to us? I wish I could say yes, but we need a couple of more mechanisms to make it work. And the reason is that the stability problem. If we just drive a reinforcement learning agent with a simple neural network, then we run into instability problem. Instead, we use an idea, not only myself, a lot of people use an idea from an article in Nature that was published in February 2015 by Google Mind researchers. What they did is they introduced a couple of additional concepts that helped to mature the concept of deep reinforcement learning as we know it today. And this includes a deep neural network and a target deep neural network. That's the first step. So there's continuous copying of values from a trained network. So that helps with stability. And then the experience replay memory just uses a mini batch of experiences to drive the reinforcement learning. So this works as a general neural network where we try to minimize the loss. We have the loss over here. We want to minimize the loss. The more we minimize, or the better we minimize, we have a better approach because we are trying to control our system with this one. Now, with all this information on machine learning, now you are wondering, where am I trying to go, right? I'm trying to go in a place where I'm going to use these algorithms in a useful way, both for the smart grid and for smart grid communications. So this slide gives a small summary of the research works I did in this area, and that relates to our talk today. So when we look at AI and smart grid, we can be talking about a couple of concepts and a couple of optimization domains in the smart grid. Load forecasting is one of them. That's a very popular area for both the academia and the industry. Residential energy management is one that we can do demand response to a fine granularity. Microgrid control is another area that I worked on a lot, and where we have where we work with multiple microgrids and control their energy exchanges. And transactive energy systems is something I will talk more about in the talk. Now, for load forecasting, actually, we have a very recent work in IEEE GlobeCon. We did load forecasting for a home. For residential energy management, that's an old work that we had done, but it is still quite, it's getting a lot of citations. So I believe it has still some information that people can benefit. Then for the microgrid control, again, it's an old work, I would say, from 2011. However, our research and many of the ideas in transactive energy systems relies on these ideas. And finally, a recent work on transactive energy systems is about power loss, basically reducing power loss when we have energy trading between the microgrids. Now, let's start talking about this topic of AI-enabled energy trading for microgrids and transactive energy systems. First of all, I mean, I gave a little bit of a summary at the beginning of or a short introduction of the idea, but let me now articulate it a little bit more. So in a transactive energy system, we have groups of microgrids that can exchange energy, which means whenever they have surplus power, surplus energy, they can either give it for free or sell it to their neighbor microgrid. And this is an implemented concept, by the way. It is not hypothetical. In Brooklyn, there is a microgrid system that uses solar power, solar generation from neighbors to power up, again, their neighbors' devices, loads, and blockchain technology is used to handle money transactions. However, making this a big scale implementation is not so easy. So most of the times people think about selling energy only to the grid. And for that, I'm from Ottawa, Ontario in Canada. In Ontario, we had a program like this. So the government at one time, I mean, it was a pilot program, it's no longer in effect, but the government was funding homes for installing solar generators, and in return, people would sell or sell at a lower price, actually not give for free, electricity to the utilities. So those are the things that are happening in real smart grids, but not so wide because of some of the challenges. Now, getting to the idea about AI and energy trading. So obviously, I mean, this transactive energy systems needs to trade energy. And as I said, it can be very complex and large systems. And whenever we talk about complexity, we love using AI because that's a technique that can help us a lot. So there has been a lot of research in the recent years. My group did a lot of research. Other groups around the world, they have a lot of research in applying Q-learning, reinforcement learning, deep reinforcement learning techniques to take care of these transactions. I'm going to give an example of one of our works, which was published and presented in IEEE COMAT conference, and the name of the paper, Decentralized Microgrid Energy Management Using a Multi-Agent Correlated Q-learning Approach. Now, this paper dealt with a single microgrid where the entities, and you can consider it, I mean, a microgrid doesn't have to be a house or a building. It could be a big campus. It could be a neighborhood as well. And imagine a campus. So there are solar panels, PVs, energy storage system, ESS, and loads, basically DSM agent. And DSM agent has some deferrable loads, which means, for example, you have a washing machine, but you can program it to run maybe flexibly within the next 3 hours. You don't specify just start now or start in 3 hours. Whenever you find electricity is cheap within the 3-hour range, get started at that time. So here the problem is PV is generating some power. Should it sell it to the ESS for storage? Should it sell it to DSM for usage? Or should it sell it to the main grid? ESS has some stored energy. Should it sell it to the main grid or give it to DSM? And for DSM's point of view, should it buy electricity from the PV, ESS, or the main grid? So as you can see here, this is a multi-agent system. We have 3 agents deciding on optimally run their systems, right? So for this, we used a technique, or actually we developed a technique that's called correlated deep Q learning. Deep Q learning is known, and I described it already. If we get into the correlated part, so once you have multiple agents acting independently, you somehow need to tame them. You cannot just leave them out in the wild and do whatever they like. You usually need some game theoretic technique, and correlated, correlated equilibrium is a generalization of Nash equilibrium. So it's very, very similar. But the only difference is that we can decide on a joint set of actions. So it's not like a one-time equilibrium that we are looking, but it's like we have a vector of actions on each agent, and each 3 of the agents in our case are deciding on optimal vector of actions for each other. Of course, as you can imagine, it would be very difficult to design such a system for hundreds of agents. And that's one of the difficulties or challenges of this work. But if you look at inside the microgrids, the number of agents are naturally limited, and that's why we can use such a scheme. So this is a one-time shot that we took from our results, and it's showing 24 hours. The first plot is the 24 hours, how the transaction happens between the entities. For example, yellow ones, I'm not going to go through all of them, but the yellow ones are when the PV is getting charged, and at the same time, it's selling some electricity. Let's look at here, for example, it's sending some electricity to the DSM and some to the grid. And what's happening with the appliances is that, which is shown on the bottom figure, that some of them, like device 1 at the very bottom, is starting at the time it is turned on, while device 2 has to be pushed to the end of its deadline. So depending on how much we push further or defer the start time of the appliances and the price negotiations, we can find a good optimal solution for these 3 agents. And we show that this correlated DQN approach is giving us better profits and costs for our agents. Now, I want to switch gears a little bit and talk about the communication sides of things, because I promised you that I would be talking about communications as well, and they're like 2 sides of a coin, right? So for that, we actually, well, this work started quite some time ago in 2016. At the time, I was at Clarkson University in the US, and if you know Clarkson University, it's in upstate New York at a very isolated town, and it has very tough winters. And the bad thing about it is that the power lines may freeze and the whole village may be isolated from the main grid. But there are 4 universities in a very small area. All of them has their generation power. But the thing is, there is no means of sharing this power, the generated electricity. So there is a hospital, police station, other critical places with less capacity of generation. Then the question was, can we form our multiple microgrids, which we called as community resilience microgrid, such that in such events, when there's a disaster that's happening, we can use the electricity from within our community. It turns out that this is not a very easy thing to do, but that was a multi-million-dollar project that had investments from NSF, from GE, and the National Grid. And I worked on the communications part of this one, and our PIs moved to Stevens Institute of Technology, and we continued our collaborations with Stevens Institute of Technology as well. And my part, as I said, was working on the communications. So once you need some tight control, like at the level of milliseconds, then you start looking at, whether our current communication technologies are good enough. You can always use a private network. Private networks, I think, when they are in non-disaster, regular situations, work perfectly. But when there's a disaster, you want to rely on an infrastructure that's already there, that has been already strengthened, like LTE or 5G. At the time, there was LTE, so this plot, for example, talks a lot about LTE, but our research goes both into LTE and 5G. So how do we make these microgrids talk and say, for example, oh, I have this many kilowatts of power available, who wants this? Oh, okay, I'm selling it for this price, or I'm giving it for free. Then, where to forward the electricity. And of course, you need the underlying distribution lines and everything, but that was the purpose why GE was into this project. So with this, we started, putting our roots into that area. And one gap we noticed in the field was the availability of a simulator. When somebody just gets into this area, they think that, oh, it's so easy, like you just combine, probably there are readily available simulators, or if not, you could simply just add some modules in MATLAB and combine 2 simulations and come up with some techniques. Apparently, it wasn't that easy. So we spent 2 years on building a simulator for integrating power grids, power grid toolboxes of MATLAB with the communication toolboxes, again, of MATLAB. And the reason why it is difficult is because power grid is a real-time system, communication network is not. But the good news is that we have this code on GitHub. So anybody, is interested in doing research on this, they can download our code and use it. And it was published, the whole idea about high reliability and multi-agent Q-learning that built on top of the simulator was published in 2019. Now with this simulator, and I think this is one of my final slides, with this simulator, what we were able to do was to simulate faults in the power system and observe the impact of the communication system in how much delays they take to deliver this faulty situation. So in this figure, we have 2 things. Actually, number one is not a fault. The dip that you see in that plot, the first dip, is the demand response request. So there is some price increase, as you see at the very bottom. And we want our transformer to send a price signal to the demand, which is at the top figure. And see how fast this demand response can help us reduce the demand. So we compare it with LTE's transmission, device-to-device transmission mode 2, so what's in the standard, and our Q-learning based technique. And we showed that our Q-learning based technique follows the ideal communication path very, very closely. So whenever a demand response command, it's almost immediately delivered to the users. And for protection, we have to look at the second or the right-hand side of the plot, where we see transformer overloading. Again, in the transformer overloading, there are little perturbations in our Q-learning technique as well, but not as much as the red line, which is the LTE's own machine-to-machine or device-to-device communication technique. So with this, we were able to show that as we make the grid smarter, as we make the communication system smarter, it is like a mutual beneficial area. We can get benefits in both areas. We can control the grid better, and with a better controlled grid, we can serve the users better. They are very intertwined systems, and AI comes like an umbrella to optimize or enhancing all these areas. Now, just to wrap up what I have been saying, these types of transactive energy systems are very promising, and utilities are making big investments in this area. Maybe sooner than we think, we're going to see real-world implementations. For control, from control perspective, AI and machine learning brings many opportunities, but not just for the optimization of the grid, but also for the optimization of communication technologies. Our biggest challenge in this area, well, there are several challenges, but if we just want to underline one of them, is that we need more data-driven approaches. So first of all, we need the data, then we need fast converging algorithms, and also we need scalable algorithms. Whenever we come for an algorithm, it has to work for tens or thousands of individual agents. So with this, I'm going to end my talk by thanking to my students. All the time, they are behind this great research. Without their hard work, it wouldn't be possible to make this presentation. And I would like to thank the audience for sticking with me, and I'd be very happy to answer your questions.
Would like to thank Professor Kantarci for this great presentation. So now we open to the floor for any